All right, today we're talking about geometric sequences and series. So what we just got done with was arithmetic sequences and series. With arithmetic sequences, we're adding some number to get the next number in the sequence. With geometric sequences, we're multiplying by some number to get the next number in the sequence. So the first thing we need to do when we're looking at a geometric sequence is to figure out what the common ratio is. What is the number that we're multiplying by each time to get the next number in the sequence? So here we can see that 3 times 2 is 6. So we're multiplying by 2. 6 times 2 is 12. We're multiplying by 2 again. 12 times 2 is 24. We're multiplying by 2. And if we were to write this as a recursive formula, we'd get a sub n equals 2 times a sub n minus 1. And of course we'd have to say that the first term is 3. So there would be a recursive formula for this sequence. For an explicit formula, let's write these a little bit differently. We want to write everything in terms of what's happening to the first term. So the first term is just 3. The second term, notice that 6 is 3 times 2. 12 is 3 times 4. 24 is 3 times 8. So let's rewrite these again in terms of our common ratio. So this is 3. This is 3 times 2 to the first power. This is 3 times 2 squared. This is 3 times 2 cubed. And so what's happening here is the nth term is going to be equal to 3 times 2 and then to some power. And notice that it's to the first power in the second term, to the second power in the third term, to the third power in the fourth term. So we want to take the number of the term n and subtract 1. And that's going to be our formula. A sub n equals 3 times 2 to the n minus 1. And if we check that, let's check the third term. If we plugged in 3 for n, 3 minus 1 is 2. 2 to the second power is 4, times 3 is 12. And so that works. And this is going to work for all of our geometric sequences. And the formula is going to be a sub n equals a sub 1, the first term, times the common ratio, which we're going to call r, to the n minus 1. So all we have to do to find an explicit formula for a geometric sequence is to find the common ratio, what we're multiplying by each time to get the next term in the sequence, and then put the first term out front here. So it's the first term times r to the n minus 1. All right. And then, of course, we can use this to find some term in the sequence. So let's say we wanted to find the 10th term in this sequence. We just plug in 10 for n. So 3 times 2 to the 10 minus 1, which is 9. 2 to the 9th is 512, times 3 is 1,536. All right, so that's how to find some term in the sequence. That works for explicit formulas for arithmetic sequences as well as geometric sequences. That's why we like arithmetic or explicit formulas. We can just plug in some number for n and find that term. This also works for sums. So if we're going to sum the first, let's say we wanted to sum the first 10 terms in this sequence. Say n equals 1 up to 10 of 3 times 2 to the n minus 1. And if we plug that into the calculator, we're going to get 3,069 would be the sum of the first 10 terms of this sequence. So 3 plus 6 is 9, plus 12 is 21, plus 24, etc. If you added the first 10 terms of that, you're going to get up to 3,069. All right, last thing I wanted to talk about is what happens if we want to sum all of the terms of this sequence. In other words, an infinite number of terms. So instead of 1 to 10, we're going 1 to infinity. Well, with this sequence, that's not going to work, right? Because our numbers are getting bigger and bigger. We're going to go off to infinity. We're going to add these bigger and bigger terms until it's just not going to, it's not going to stop at any specific number. It's just going to go to infinity. So we can't do that with a term like this, with a sequence like this. But let's say we have a slightly different sequence here. Let's say that we've got a sequence like this: 4, 2, 1, 1/2, 1/4, etc. Well, can we add all the terms of this sequence off to infinity? Well, let's think about it. 4 plus 2 is 6, plus 1 is 7, plus 1/2 is 7.5, plus 1/4 is 7 3/4, plus 1/8 is 7 7/8, plus 1/16 is 7 15 16ths, plus 1/32 is 7 31 32nds. So hopefully you can see what's happening here. We're getting closer and closer to a single number. And at infinity, we're going to say that, in fact, we reach that. If we added all of these terms in this sequence, we're going to get to 8. That these are all going to add up to 8. All right, so this only works if our common ratio is less than 1. If the common ratio is less than 1, then we're getting smaller and smaller, and we can actually add up terms of an infinite series. So in this case, our common ratio is 1/2. Right? We're multiplying by 1/2 each time. And so our explicit formula for this sequence would be a sub n equals 4 times 1/2 to the n minus 1. Well, it turns out that there's a very nice formula for an infinite sum. Because if you plugged this into your calculator using sigma notation, it's not going to let you plug in an infinity sign and do that for you. But we're going to say that the sum of an infinite series, where the r is less than 1, is going to be equal to the first term divided by 1 minus the common ratio. So make sure that you know this formula, because it's really handy. If we did it for this series here, this sequence, if we added up all of the terms of the sequence, we're going to get the first term, which is 4, divided by 1 minus, we said our r was 1/2. 1 minus 1/2 is 1/2. And 4 divided by 1/2 is the same as 4 times 2, which is 8. And that's how you add up an infinite series, so long as our common ratio, the r, is less than 1.